Okay, welcome to chapter 3, homework key. Let's look at number 31 first. Number 31 says the bond in Cl2 can be explained by end-on overlap of two p atomic orbitals. And it wants us to know, wants to draw the bonding and anti-bonding orbitals. So for just a p orbital, remember what does a p orbital look like? A p orbital just looks like this. We're talking about chlorine here. And one side is shaded, one side's not. So if I bring together two chlorines in a bonding scenario, okay, as pictured in the textbook, okay, the bonding MO would look like this, right? My shaded ends overlap, and I kind of shaded the middle part to show that's all overlapping. If I bring them together in anti-bonding, it's basically the shaded side on one overlaps with the unshaded on the other. Okay, so these are both sigma symmetry because they're just end-on overlap. There's just one lobe of each orbital overlapping. There's not a two-lobe overlap like in a pi bond. Okay, 33, and we would say these have sigma symmetry. I don't know if I said that yet. Okay, 33 wants to know the geometry and the hybridization on each atom that's not a hydrogen. Okay, so this one is sp3 and tetrahedral because it's a carbon with 4 things attached to it. This one is a carbon with 3 things attached, so that's only sp2, and that is going to be trigonal planar as our geometry. Okay, this one again, we have an sp3 carbon. Hopefully we can see that. This one is a little harder to see. Okay, we have 3 things attached. We also have a lone pair, which is taking up one of our slots. Okay, so that lone pair is going to go into a hybrid orbital. So this is still going to be an sp3 carbon that has a negative charge on it. Okay, so these are both tetrahedral then. Okay, next one, I have a double bond oxygen. So that's double bonded carbon. Okay, so that's sp2. This oxygen also has 1 double bond and 2 other things, total of 3 things attached to it. So it's going to be sp2 as well, right? We have 3 things, 1, 2, 3, s, 1p, second p would be 3 things total to match that. So these are both trigonal planar. Okay, here again we have a sp3 tetrahedral carbon. We also have a nitrogen with 4 different things attached. So that's an sp3 nitrogen. Both of those geometries are going to be tetrahedral as well. Okay, then this one we have another tetrahedral carbon, another sp3 tetrahedral carbon, and our oxygen in this case, okay, also has 3 different things, 4 different things attached to it, right? 1, 2, 3, and then 4 counting the lone pair. So this is also an sp3 tetrahedral oxygen. Okay, remember we can have hybridizations for things that aren't carbons. It doesn't have to just be carbon. Okay, last one. This carbon, I didn't draw out the geometry, but this carbon has 3 or 4 groups total attached to it, right? 1, 2, 3, and 4. So this guy's sp3 and tetrahedral. This one only has 2 things attached. So 1, 2, right? It's a triple bond carbon. We know those are sp. This one also, okay, this has a lone pair here to give it this negative charge. So this is also going to be an sp. It has 1, 2 groups attached to this carbon, okay, and that's what we get for sp. And these are both then going to be linear carbons. Okay, hopefully that wasn't too bad. Next one, counting the number of sigma and pi bonds. So don't forget about your hydrogens here. I'm going to count my carbons first, then I'm going to count my hydrogens for my sigma bonds. Okay, let's do the pi bonds first. I think pi bonds would be easier to count for us first. Okay, so my pi bond. Okay, sorry, I had a little technical hiccup there. I think I was counting my pi bonds. My pi bonds, I have 1, 2 pi bonds. Okay, so that's not too bad. My sigma bonds have. Okay, this is where we're going to resume. So clapper action. Okay, I had my structure drawn incorrectly. So C to C bonds, I have 1. So if I look at just the single bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, plus these single bond, right? These that are part of these sigma bonds that are part of the pi bonds. So 15 C to Cs. H's I have 25, 3, 6, 7, 9, 11, 14, 15, 17, 19, 21, 24, 25, and I have 1 O to H bond. And I also have one O to C bond. Okay, so that's a total then of 42 sigma bonds for this molecule. So it'd be quite a big MO drawing if we had to do one for that. Which is what we have to do on the next one. Okay, so this one, the first thing was to sketch the MO picture of this. Okay, basically, the important thing for me here would be that you show the pi bond. So this has a pi bond, and then these two have a pi bond that's perpendicular. So one of them could be like this. Okay, these p orbitals that are in the plane of the paper overlapping. This one, it would have to be the p orbitals that are not in the plane of the paper overlapping, right? Because this guy can't use the same p orbital to make both of these double bonds. So the middle carbon will use the in-plane p orbital on this side, and it'll use like a perpendicular p orbital on the other side. Okay, I'm not the best at drawing, so I'm not even going to try to draw it. There's a picture in your solutions manual. You can check that out. But we will talk about this MO diagram, okay, the MO energy level diagram. So remember, for this class, we're doing the simplified version. We just need to figure out how many sigma bonds, how many pi bonds, and how many lone pairs do we have. And then we'll always go sigma, pi, lone pairs in between, and then pi star, sigma star, right? So sigma, pi star, sigma star, lone pairs go in the middle. Okay, how many pi bonds do we have? This one has 2. How many sigmas? 1, 2. Remember, this is a double bond is a pi and a sigma, so 1, 2, 3, 4, 5, 6. And how many non-bonding then would just be 0. Okay, now to draw this, I have 6 sigmas, so 1, 2, 3, 4, 5, 6 that are all equivalent. So 6 sigma, and I'll say that they're filled since I don't care so much about those. Okay, then at my pi bonding level, I said I have 2 pi bonds. Okay, and those are going to be degenerate or equivalent to each other. So 2 pi, which are also filled. That I'm going to actually show by adding my electrons. Okay, then I have my pi star level. So 2 pi anti-bonding, which are empty. And then finally 6 sigma anti-bonding, which are also empty. So this is my MO picture. Okay, this would be my LUMO, my unoccupied molecular, the lowest unoccupied, and then my HOMO would be this one, my highest occupied. Okay, so pretty simple compared to what we did in 241. Pretty simplified. Stupid camera, if I can get it in place. Okay, last one, 52, wants to know which of these two is a stronger bond to the chlorine. Does this one have this sp3 carbon? And it didn't label this, but is this sp3 carbon to chlorine going to be stronger, or is this sp carbon to chlorine going to be stronger? Okay, the sp carbons, because their hybrid orbital, right, is what this sp hybrid is what's going to make the bond with this chlorine. Because the sp hybrid is like really bulbous, it's more S character than the other ones, like a sp3, right? This one's only got 25% S character. This one has 50% S character. Right? It's just a mix of an S and a P together. This one's going to be a lot more bulbous. It's going to resemble more like an S orbital, and S orbitals are really good at sigma bonding because they have all that electron density kind of localized in the same spot. So this is easier for overlap with than the P orbital of the chlorine. Okay, we'll get fuller overlap between these two than we would if it was an sp3 and it wasn't quite so bulbous on this end. Okay, so SPs overlap better and they tend to make stronger bonds. So that key was short and sweet. I'll catch you in the next key, hopefully.